co-host?
I don't know. Participants.
Yeah.
Is it? Well, actually, I am a co-host. He's the host.
Okay.
All right.
So I think he have to grant you.
So yeah, Mohammed, are you there?
Sorry, yes, I am here. Sorry, I just logged in earlier. Sorry.
Yeah, appreciate that. And I think we're going to have to, I think because you logged in first, you are the host. I'd like to switch our roles. So
Yes, yes, sure, we can do that. Let me try to go over here to participant, and I think I can do something here. Make host. Yep. Yes, I think now it should work. Hopefully.
Okay. So and then we have
I
to
am the
grant
host.
Mohammed as co-host.
Please make co-host. Make co-host. Sweet.
Yeah.
All right. Now the question comes. Oh.
Okay.
We're gonna go drop our stuff off in the control room. Do you have anything here?
Okay.
Do you have any-
So just to basically
Hi, Andrew. Hi.
just
He I think he signed up for in person.
okay.
Yeah.
So what I'd like is, so what's going to happen is, assuming we have virtual folks, then Patrick is going to go through a presentation, basically a normal closed dome sort of thing.
Okay.
And we are going to bring these folks up to the roof and howdy, folks, and welcome to Evening Under the Stars here at George Mason Observatory. My name is Dr. Rob Parks. I'm the Deputy Director here, and I will be the MC for this evening. Thank you for bearing with us. We're still transitioning from a entirely virtual event due to the pandemic to now a hybrid event where we have both in-person and virtual guests. So, without further ado, what is going to happen is we're going to have M is going to be our speaker today, and he is going to give you a presentation on black holes. And after that presentation, there's going to be a short Q&A. And then once he is done, we're going to essentially split. The virtual folks are going to have a essentially tour of the observatory in terms of seeing images that we have taken through the telescope and just hearing about the telescope in general, what we've been able to do for it. You all who are in person, and thank you for again for being here. We're going to take you up on the roof. Unfortunately, the weather looks iffy. We're going to try to open up if we can, but we may in fact be limited to just simply showing you the telescope, talking about the telescope, and showing you the control room, which is on the roof of this building. So as you can see here, the control room is on the roof. The telescope itself, the 32-inch telescope on itself, is on top of the silver tower. I truly, every time I do this, I tell myself that I need to update this slide. These images that you see here are from our own telescope. These are images taken by our own students, specifically the undergraduates. And what they've done is they have done a rather challenging, this is not simply just a normal, say, iPhone photograph. These photographs are taken using a blue filter, a green filter, and a red filter, and then color balanced and combined. And so that tends to be very challenging. But this is some of the earlier results that we've gotten from this. And it also gives you an illustration of what sorts of objects we can actually see here in George Mason, even though we have tremendous light pollution. Evening Under the Stars is, Evening Under the Stars is our public night, which we host, roughly speaking, this semester every alternating Tuesday evenings, although it's been less alternating and more just sort of random. But as I said, the way that this works is we're going to have a 30 to 45-minute talk on IM, Q&A, and then we're going to give you a guided tour of the observatory for those of you in person. This is not a one-person operation. We have many people. It takes many people to do what we do here at the observatory. We have myself. We have the director of the observatory, Peter Plavchan. We are blessed with having 4 graduate assistants who are really the work people that do most of the work. There's there's Kevin, there's Mohammed, there's Patrick, who's also in the audience. And then we have a slew of undergraduate tour guides, S back there, Emmy we have, and also Jonathan, who is not only that, but Jonathan is also the president of the Friends of the Observatory. I don't know if that QR code actually works, but I thought I'd just put it up there. The Friends of the Observatory, or PHOTO, is a very active astronomy club on campus. They are frequently taking out the solar telescope out near Johnson Center or wherever elsewhere on campus, so people can actually look at the sun through a protected view. Also, they've been known to bring out our telescopes out into the fields and also show people night sky views. And in addition, if you are a PHOTO member, you can participate in the PHOTO nights that we have here at the observatory, and the students are essentially allowed free reign to look at whatever they like using the 32-inch telescope under supervision. So if you are a student here, or you're a student who is currently on virtually, I highly recommend looking into this organization. If you would like to know more about what we do here at the observatory, I also suggest you subscribe to The Moon, or the Mason Observatory Outreach newsletter at science.gmu.edu/observatory. This is a monthly periodical that contains a list of public events, not only our public events, but also public events through the Northern Virginia Astronomy Club. So that club also puts out public nights where they have their own telescopes that people can view. So there's a listing of that. There are articles about the constellation of the month. There are student highlights, and they also talk about projects that we do here in the observatory, particularly outreach and research-wise. And occasionally, if I remember, I will also put in a space news section as well. If you like what you see with our observatory and you really want to help us grow, particularly in terms of the outreach aspect of our work, one of the things that I am truly trying to get off the ground is we have an inflatable planetarium that is portable. And what I really like to be able to do is take that to elementary schools, middle schools, possibly even high schools in the area that simply do not have the resources in order to see or experience a planetarium show. That, of course, requires a bit of the funds. So if you're interested in helping with that, I would ask that you consider being a patron of our observatory at whichever level you prefer. With that out of the way, I'd like to introduce M. Thunyapong. He is a fourth-year PhD student here at GMU. He finished his undergraduate studies at the Aerospace Engineering at, let me see if I get this right, Chulalongkorn University in his hometown of Bangkok, Thailand. Before coming to the US to pursue his dream of studying physics and astronomy, he is currently a GTA, as I said, here at the observatory, and he's doing research with Dr. Peter Becker on modeling a black hole X-ray source. Now, more on this subject, I will turn it over to M, but I will, let me switch out. Oops. How do I get out of this? Here we go. Go that. Slideshow. Start. Screen. And you are good. So take it away.
Okay. Thank you, Dr. Parks, for the introduction. And greeting everyone from here, the Research Hall 163, and from Zoom. Let's get started. Today's talk, I'm going to give you a talk about holes in the sky and what's on the edge. And specifically, I will divide my talk into three parts. I first give you an overview, what black holes are, what are the components, and what are the types of black holes. Then we shift our focus into the galaxy that hosts those black holes in the second part. In the last part of the talk, I will introduce you to a black hole I used to model in my research. It's called 1H0707495. That's a long name. I introduced some other concept involving this, such as X-ray emission, time lapse, before we end with the result I found in my model, the wedge-shaped accretion disk model. Spoiler alert, this talk may give you some melanoheliophobia, or the fear of a black sun. And let's get to the first part. So when we talk about black holes, this concept is vaguely introduced to us in late 17th century. There's an English philosopher, John Mitchell, who introduced a concept of a dark star. He proposed that if there is an object, the escape velocity on that surface is so high that it is equal to the speed of light, that object may not be seen because the light cannot escape. And some other time, another French mathematician, Pierre-Simon Laplace, also came with the similar idea in almost 1800. He came up with the same ideas, and we kind of use this idea nowadays as it inspired a lot of physicists to think about what a black hole really is. Although this model is not very accurate because it's just a Newtonian physics, doesn't include general relativity, but I feel like this can give you some sense of what the black hole really is. And to demonstrate this, let's consider the escape velocity itself. You may have come across this word multiple times. What goes up must come down. This word actually true for an object we fire up with low speed. If let's consider jumping from the ground, you input some initial velocity or initial kinetic energy, and you go as you go up, that energy is converted to gravitational potential energy. So at some point you lose kinetic energy or velocity, it becomes zero. And if we kind of model that using equation, we've found this in some physics high school subject. We rearrange this equation. We find that escape velocity, the velocity that you initially jump up, this escape velocity also relates to the point where you can escape, or the gravitational potential energy becomes zero. That escape velocity depends on the mass of the planet and the distance from the center of that planet. It doesn't depend on our mass at all, as you can see from the formula here. G is just a gravitational constant, the m is representing mass of the planet, and r is the distance from the center. So you can imagine that if we plug in some high value in the right-hand side, in the left-hand side of the equation, like speed of light, the right-hand side of the equation has to be huge as well. So if you plug in speed of light here for the escape velocity, we must have higher mass of the planet, or it must have a very short distance, or that object has to be very compact. Not only that, if we rearrange this equation can also tell us some distance that is corresponding to the escape velocity that is equal to the speed of light. And coincidentally, this distance is equal to what is called Schwarzschild radius. So the Schwarzschild radius is the radius of a black hole. We can vaguely say that. It is a crucial parameter to the solution to Einstein general relativity equation proposed by Karl Schwarzschild, the German physicist. He proposed this in the same year, 1915, the same year Einstein published his general relativity. So if we assume that the black hole doesn't spin, doesn't have charge, and follows a set of physics, we can approximate that the radius where light couldn't escape from black hole, or we call it event horizon, is equal to this radius, Schwarzschild radius. We can also group this term GM over square C and make it as a unit called gravitational radius, RG. We will use this kind of unit for the sake of convenience, although this I have to remind you that this unit may not be constant for different star because it depends on the mass of the star. And by plugging in some values we know and we compare to the mass of the sun, we can conclude that if we were to shrink the sun to a black hole, the sun will have the Schwarzschild radius of about 3 kilometers. So that's very, very compact. So we can safely say that this 2RG is the place where event horizon is placed. Event horizon is kind of analogous to our normal horizon. So something that's set below the horizon cannot be observed. So something that is set closer than the event horizon cannot escape black hole. And what we see here, we also have what we call photon sphere at 3RG, 3 gravitational radius. And it corresponds to the point where photon can have stable orbit around black hole. Photon is a simple, it's a term for light particle. Although I said it's 3RG, it appears at 5 something RG because of the relativistic. So that should be noted. And we also have the innermost stable circular orbit, or ISCO, at 6RG. It corresponds to the location where massive particle or particle with mass can have the stable orbit closest to the black hole. And this component of the black hole is called accretion disk. It's where mass of the stars or nearby gas that is pulled by the gravitational force of black hole get accumulated and orbit around black hole. This kind of component is very hot, so it produces radiation, and we can observe. Therefore, we can observe or see the accretion disk of the black hole. The last component I have here is the image projection of the accretion disk. The projection can come from either under the accretion disk, as I point here, or it can be seen here above the accretion disk due to the effect of gravity of general relativity. What I didn't show there in the last slide is two more. It's another component of the black hole. It's called corona. So this corona is mysterious to astrophysicists because we are not sure how it is actually formed yet. It's just as mysterious as the corona of our sun. But based on our current understanding, there are two main models for corona. Either they can be on the pole of the black hole. We call it lamppost because it goes vertically like a lamppost, or it can be spreading around the black hole in the extended model. Note that the accretion disk and corona is not exclusive to black hole. It can be found in other active objects such as accreting white dwarfs or neutron stars, or the object that is consuming another stars or gas. Since we don't know about the corona, but do we know how the black hole was formed? So far, we have 4 major types of black holes. The first one is primordial black hole. We never actually detected, but it's a hypothetical black hole because we think that in the early universe, at some point the particles may be packed together so dense that maybe sometimes light couldn't escape and form this type of black hole. But since this type of black hole also have a short lifetime, we haven't been able to detect them. Next one is stellar black holes. This one is formed by a dying star. So for a star that has a mass 3 times massive than the sun, or 3 solar mass, to about 100 solar mass, it is massive enough such that when it runs out of nuclear fuel, the fuel that used to oppose the gravity, once it run out of this field, it collapsed by its own gravity, its own weight. And that gravitational force is strong enough to overcome the pushing force of electrons or neutrons, and it forms something that we don't have a model yet, and that thing is black hole. So black hole is stellar black holes. We don't know about what is inside, not only because it's not emitting any light, but because it requires other models about our about fundamental particle physics as well. Next, I have supermassive black hole. So we believe that this kind of black hole is at the center of every galaxy. It can have the mass above 100 solar mass up to like millions of solar mass. It's very, very massive. Despite that, it's the formation of that is not known, because we think that this kind of black hole can be formed by smaller black hole merging to become this massive. That leads to the last type of black hole, the intermediate mass black hole. We think that before it forms the supermassive black hole, we should be able to see intermediate sized black hole. But so far, this type of black hole is rarely to be found. And so intermediate sized black hole is the black hole with the mass between the supermassive black hole and stellar black hole. Oh, I think I may have the scale here wrong. The supermassive black hole should have the mass about 1 million times, and this should be the scale of intermediate mass black hole. Okay. And now you may ask, how do we observe black hole? So in previous a couple of slides ago, I mentioned that we can see the accretion disk of the black hole. So that's one thing we can do. The recent viral black hole image in 2019, it shows the accretion disk of a supermassive black hole M87. This is recorded in radio frequency. So to give you a quick summary of the frequency of light spectrum, you can imagine light as some vibrating particle, or we like to call it photons. The light or photon that has lower energy can be will be shown in red, and then you can remember the color from rainbows, right? Red, orange, yellow, up to violet. Violet is the highest, is the light with highest energy. So something, so light with the energy lower than red light, we call it infrared. Lower than that, it is microwave and radio wave. For the light that has higher energy than violet light, we call it ultraviolet, X-ray, and gamma ray. So the way astronomers observe this supermassive black hole is they can look at the jet at different kind of energy of the light, can be radio wave, visible light, or it can be something in ultraviolet and X-ray. But this image is constructed by using the array of radio telescope that is equivalent to the size of the Earth. So we are required the telescope with the size of the Earth to take the image of this black hole, and it doesn't give us all the components we need. We see only the accretion disk, not the corona. But so now you may think that how do we see other kind of black hole? So for the black hole at the center of the Milky Way, Sagittarius A star, recently we just have the image of that, but it's still very hard to be seen. The alternative way is that we can track the object orbiting around this black hole, the star that orbiting around the supermassive black hole. And by calculation, we can calculate the mass, and we can somehow conclude that this object can be a black hole. Another method is to use the property of light bending, or we call it gravitational lensing. When a black hole passes through the background star, it deviates the light due to the curved space. This is because of the general relativistic effect, and it can be difficult to look sometimes. I didn't include the merging of black hole. That is another story, but for merging black hole, we can also use gravitational wave to detect those black holes. But now what I want to do is I want to shift our focus to the place that hosts this kind of supermassive black hole. We will focus on supermassive black hole, and although it's called supermassive, when compared to the size of the galaxy, it can appear just a tiny dot. So most of the time when we observe this supermassive black hole, we observe the galaxy itself. Although if you want to observe the supermassive black hole further, that object needs to radiate some high energy. So we will also narrow down to focus on what is called active galactic nuclei. So if we assume that at the center of the galaxy is supermassive black hole, and it is consuming some stars and radiating some X-ray, we set it to be active. And when we see the galaxy, like in this image, we see that sometimes the viewing angle from us to that galaxy can be either face on. You can you can see from the center of this image. This is like you looking it from the top view, or sometimes it can be edge on, or you looking at the side of the galaxy, or it can be somewhere in between. This active galactic nuclei, or AGN, is also based on the viewing angle we have to that galaxy, and it can be further divided to two types, either radio quiet or radio loud. For radio loud, by its name, it means that active galactic nuclei, or AGN, is producing radio wave, while the radio quiet AGN produce weak or no radio wave. For radio loud AGN, if we look face on, we look through the jet of the black hole, and we will detect strong X-ray or gamma ray. We call it laser. If we look from other angle, we get what we call quasi-stellar object or quasar. This one will be called a radio loud quasar. On the other hand, if we look at the AGN face on, and this AGN happens to be radio quiet AGN, we would get radio quiet quasar. If we look at some other orientation or viewing angle, we set it to be a Seyfert galaxy. So Seyfert galaxy normally looks like just a normal spiral galaxy, but at the core it shines bright in UV or X-ray. The name is after Carl Seyfert, who described this property in 1943. It can be further classified to Seyfert 1 or Seyfert type 1 or Seyfert type 2, but I will probably not go into that detail. Sometimes the division line is not that clear. What is shown here is some example of the Seyfert galaxy. This is called New General Catalog, NGC 6814. This is NGC 3081. So as you can see, it is a spiral galaxy. But if we observe it in X-ray or UV range, or this portion of the spectrum, we will receive some signal, bright signal. Okay, so let's move to the object that I focused on my research. So in my research, I focus on this object. It's called 1H0707495, and it's also known as PGC. So that stands for Principal Galaxies Catalog 88588. It is said to be Type 1 Seyfert galaxy. So Dr. Peter Becker and I work together, and we use the observational data from other authors and try to model what's going inside. This image shows the actual image taken in visible range. So as I mentioned earlier, when we look at AGN, we actually look at the entire galaxy. It appears as a tiny dot, not very spectacular. It's impossible to see what's really inside the black hole. It's impossible to see how the accretion disk or corona based on this viewing. And it's in the constellation of Puppis, the stern deck of Greek mythical ship Argo, and the magnitude is around 16. So magnitude is the measurement of brightness. This means the brightness of this object is not so bright. It's as bright as the asteroid in asteroid belt. You cannot see it with your naked eye, but with a telescope, with a telescope and a clear night sky, it can be seen clearly. The size of the supermassive black hole is about million times the mass of the sun, mass of our sun. And its distance is 590 million light years away. So we get the, or not we, other observational astrophysicists get this data from XMM Newton. It is the X-ray space telescope launched by European Space Agency, or ESA. It shows a number of X-ray spectrum, but in our study we focus on X-ray fluorescence. So this kind of process occurs by some electrons in the inner shell of an atom get bumped, and when it gets bumped, it means some space is taken out from that shell. This vacancy induce other electron from the higher energy to come down. You can think of it as booking a hotel. If someone, well, this hotel happens to be very popular in the first floor, and the floor higher than that is not so popular. So when a person or some people from downstairs go out from this hotel, other from the upstairs want to come down. And if you imagine like that, the energy we are talking about is the gravitational potential energy, right? When you live in the higher floor, you have higher potential energy, and when you come down, you have to it means you lose the energy, you dissipate some energy. But for the atom, it dissipates that kind of energy in terms of radiation, or in this case, X-ray. Another X-ray emission we have in our research is called Comptonization. It's a kind of scattering. So scatter, it's like playing some the pool. You have something hit the ball and the ball gets scattered, right? And in this system we have light particle or photon. It hits electron, and for normal comptonization, the electron gain energy from the photon, and the photon hitting that electron lose energy. But there can be in opposite scenario, we call that inverse comptonization. A photon hits an electron, and electron loses an energy to that photon. The X-ray emission can also come from Bremsstrahlung emission. The word Bremsstrahlung is a German word, literally means breaking light. It's a light from a deceleration of a charged particle, in this case, electron. When it gets too close to a nucleus of atom, its velocity changes. Therefore, it has to emit some energy out in terms of X-ray. Last but not least here, for almost other kind of radiation, it follows some model called blackbody radiation. So blackbody radiation is a kind of thermal radiation. Anything that has temperature above zero, absolute zero, or 0 Kelvin, or if you use degree Fahrenheit, that's -460, and anything that has temperature above that emits some light. Like we ourselves we emit infrared light at our body temperature. So in this photo, it's a horseshoe emitting red light or orange light at about 1500 degree Fahrenheit. So you can imagine that something that emits X-ray has to be very, very hot. And when we look at the signal of X-ray at different energy, in this case, we divide it to relatively low energy X-ray and relatively high energy X-ray. We call the lower X-ray, lower energy X-ray, So we call the lower energy X-ray soft X-ray, while the higher energy X-ray hard X-ray. And once we look at certain time scale, we see that the signal has some similar resemblance, but it has a delay, or we call it lag, or some lead in our plot. And it's weird that when we look at some short time scale, the soft X-ray lags the hard X-ray. But if we look at longer time scale, long enough, we see that in general, hard X-ray lags the soft X-ray. So we use a mathematical tool called Fourier transform to decompose the signal into sine wave. So Fourier transform, in mathematics, we say any kind of signal can be written as a form of sine wave. So if we decompose that signal to sine wave, we can record it in terms of frequency. And that helps us in many applications. For example, in noise canceling technology, we also use that to decompose sound frequency to various sound signal to various frequency, and then we get rid of unwanted frequency, and then we can recreate that sound wave. But in this case, the information about the frequency helps us to understand what is going on in between the hard X-ray and soft X-ray. As you can see in this plot, we say that this region is corresponding to hard lags. So this is the lag that caused by hard X-ray, while the other side of this plot is the lag caused by soft X-ray. Notice that this axis of frequency, if we look at lower frequency, that means it has higher time scale. It corresponds to this plot a slide ago. So at longer time scale or shorter frequency, the hard X-ray lags soft X-ray, while the shorter time scale, the soft X-ray lags the hard X-ray. It puzzled astrophysicists 12 years ago, and many models have been proposed since then to explain why there is a lag between those two energy of X-ray. Like I mentioned when we discuss about corona, there is two main models, either extended model or lamppost model. In both models, it's assumed that the hard X-ray is produced by the corona itself, while the soft X-ray is the reflection to the accretion disk, and it comes to the detector later. So if anyone had been here in the Evening Under the Stars in April, the one that features Dr. David Borman, he also worked with Dr. Peter Becker. They form a model called quasi-spherical corona. This model assumed that some region closer to the black hole, matter start free falling into the black hole. And they think that the soft X-ray should somehow be produced inside, not because of the reflection, but because of the Comptonization, and it can be a Comptonization or invert Comptonization. What I use in my model is we modified that shape a little bit. Instead of saying that the matter is free falling into the black hole, we said it should be a wedge shape spiraling into the black hole. By spiraling, I mean like this, if you look at it on from the top. So matter should slightly fall into the black hole instead of free falling into the black hole. Free falling means something that fall inwards to the center. So it has no component of radial velocity or the component of orbiting velocity at all. And but so far, our model still has to be verified to get close to the observational data and to get close to the former model. The blue line represents the observational data. The red one is our wedge-shaped model, and the green one is the quasi-spherical corona. Okay. Before I end this talk, I feel that this can be intimidating to include, but this is the actual equation I used. Dr. Becker and I used to calculate the flux that is responsible for this time lag. So basically, it means it includes all kinds of quantization plus the source photon. So source photon can come from the X-ray fluorescence or other types of X-ray emission inside the corona, and it gets transformed according to this equation. And this work is partly analytically. We have to solve this equation, trying to simplify it, and we also solved it numerically using Wolfram Mathematica. This is the example of how we optimize the result. We play around with some variable, for example, the velocity, the mass flow rate, and so on. So in conclusion, today's talk, I give you some overview about black hole. Black hole is a mysterious object. So far, we can only detect stellar and supermassive black hole. And we focus on supermassive black hole, especially one that is eating a star. We call it active. Unfortunately, we cannot picture all the supermassive black hole. Rather, we just have the image of the galaxy that hosts this black hole called active galactic nuclei. The one active galactic nucleus we have, 1H0707495, produces some bright X-rays, and that X-ray signal exhibits the time lag between X-ray energy. We use this lag at different time scale to model what should be on the edge of the black hole, i.e., what should be the shape of the corona or accretion disk. And based on the former model, it looks very promising, but we hope to get the parameter more realistic with our current model, the wedge-shaped model. And thank you for for listening. If you have any question, please feel free to let me know.
So does anyone have any questions for M? Oh, yeah. Go ahead.
Yeah, there are some other studies on other objects, but I guess this object has a unique kind of time lag, and it's something we want to focus. Yeah, some object might not have like the frequency we want to observe, the frequency that is corresponding to the time the X-ray signal or the flux we used to input in the equation. Yeah, hope that answers you.
My question would kind of piggyback on top of that. Do you know, so once you've mastered this particular black hole, do you have your sights set on anything else, like any other black holes of this type, or?
I still working on this black hole. I don't have any plan to apply this to other system right now. We're trying to get this data more and more realistic first.
Okay.
Yeah, there are I think there was other kind of interesting study, like for other system, they may hypothesize that the corona may be like the lamppost model that I explained. They create a geometry of that corona based on the time lag. They try to think that if this kind of corona how long it should extend from the black hole. But I think that kind of system is somehow similar, somehow different to this system. Yeah, so I think different objects behave also differently. Some object may have like changing corona. Yeah, so we just want to focus on this kind of object first.
Okay. Does anyone have any other questions for him? Yeah.
That hard soft, is that like, I know you're doing X-ray, but it's like the hard closer to, what is it, gamma, and then soft is closer to ultraviolet? Is that what roughly?
They are both X-rays. But I can show you.
Yes, all the numbers.
Yeah.
So the hard X-rays are higher energy, and so
Yeah.
yes, they would be closer to the gamma ray regime.
Yeah.
And
It's closer, but yeah, it's still the X-ray. Maybe they are produced by different shell of the atom. Yeah. So specifically in this object, we use the ion K alpha line and L alpha line. So we name the shell of the atom from the inner to the outer as KLMN. So K alpha means the X-ray is corresponding to the changing of L line to from L shell to K shell, and for L alpha, it means it is corresponding it is corresponding to the transferring of the electron from M shell to L shell. And this kind of X-ray can have different energy or frequency. And I think the frequency we use here is still corresponding to X-ray emitting from the iron atom. Yeah, I know this is a long answer to your question, but just to give you more sense about the how wide the X-ray is.
Okay, well, if we can thank him again. Now we will effectively split, and I will ask Emmy and Jonathan to bring our folks up to the observatory. And I will then talk to the folks online. All
Do we have some questions?
Oh, I forgot that you were looking at it. No, we have someone who's thanking you. Excellent.
Thank you very much for joining.
Mohammed, are you there?
Yeah, I'm here.
Excellent. So what I'd like you to do is, if you could log on to the system, log on to the observatory system. And basically what I'd like you to do is I'd like you to share your screen of the observatory screen and just kind of give them a brief overview of what our observatory is and what it does and that sort of thing.
Okay, I'll try that. I recently have some issues with logging in, but I will do my best for now.
Okay, appreciate it. Thank you. All right, I'm going up to the roof, so I will see you all later. Right, I'm going to
Dr. Rob, you are here? I think I'm able to share my screen. Please, could you confirm if you are able to see my screen now?